What do party balloons, neon signs, and certain light bulbs have in common? They are all filled with a noble gas. The noble gases are the group 18 elements: helium, neon, argon, krypton, xenon and radon. These elements are notable for having a full valence shell of electrons. Helium has 2 valence electrons, whereas, the other noble gases each have 8 valence electrons. The noble gases all have full valence shells, which makes them very stable elements. In fact, they are so stable that, in the past, chemists thought that they could not react with other elements, which is why they were called the inert or unreactive gases. The full valence electron shells of these atoms make noble gases extremely stable and unlikely to form chemical bonds because they have little tendency to gain or lose electrons. Although noble gases do not normally react with other elements to form compounds, there are some exceptions. Xenon may form compounds with fluoride and oxide. First example is xenon difluoride. When a mixture of xenon and fluorine in the ratio of 2:1 is heated at 400 degrees Celsius in a sealed nickel vessel, XCF2 is formed. Xenon has 8 valence electrons, while fluorine has 7 valence electron. And we have 2 of these fluorine. So, 7 times 2. And this gives us a total of 22 valence electrons. Next step, we will put xenon as our central atom because it is less electronegative than fluorine. And let's put 2 fluorine on either side bonded with single covalent bonds. Each of these fluorine already have 2 valence electrons. So we need to give each of them 6 more. So, we have just allocated 18 valence electron. And we still have 6 valence electrons to allocate, and there is only one place where we can allocate those leftover 6 electron, and that's at the central atom, xenon. So, let's do it. Now, we have the Lewis structure of xenon difluoride. What's interesting here is our fluorine, they have an octet of valence electrons. But what's going on with xenon? Xenon has 10 valence electrons. So, this is one of the examples of exception to the octet rule, where we go beyond 8 valence electrons, which is possible for elements in the 3rd or higher period. Next is xenon tetroxide. XCO4 or xenon tetroxide is a chemical compound made up of xenon and oxygen. Xenon has 8 valence electrons. Oxygen has 6 valence electron. And we have 4 of these oxygen. So, 6 times 4, and this gives us a total of 32 valence electrons. Now, we will draw the skeletal structure of the molecule with all the atoms joined through a single bond. As xenon already has a complete octet, the main focus here is to satisfy the octet rule for the oxygen atom. As every single bond represents one shared pair of electrons, it is clear from the above structure that all the oxygen atoms are in short of 1 electron each to complete their octet. Therefore, they form a double bond with the xenon atom by sharing 2 electrons and acquiring a stable state by completing their octet. This sharing results in overfilling of the valence shell of the xenon atom, which now consists of 16 electrons, but as xenon has its valence electrons in the 4th energy level, it has the access to 4d sublevel and hence, is capable of accommodating more than 8 electrons. All of the noble gases are colorless and monotonic, meaning that they exist as single atoms. Moving down the group, the number of electron shells increases by 1 shell. Hence, the further down the group, the bigger the atom. The size of the atom also affects its boiling point. These boiling points increase because intermolecular forces between larger atoms with more electrons are greater than that between smaller atoms with fewer electrons. Also moving down, the density of the gases increases because larger atoms take up more space in a set volume. So now we know the basics of noble gases, the group 18 elements, also known as group 0. Their stability is one of their main characteristics, allowing for many real-life applications.